So, welcome everybody to a special timing seminar today. It's special in part because it's coincide with the Tripod's distinguished lecture. It's also special because we are honored to host David Donoho, professor of statistics at Stanford University, and the Ann T. and Robert M. Bass professor of humanity and sciences there. So Professor Donoho has won many awards over the year, which I would only mention the MacArthur Fellowship in 1991, the Shaw Prize in 2013, and the Gauss Prize in 2018. His research interests include the mathematics of statistical inference and scientific and signal and image processing, with important contribution in multi-scale geometric analysis, wavelets, and compressed sensing. Today, well, taking it from here, it will discuss singular values thresholding.
So first of all, it's a big honor to be invited by someone you really respect. And Simon Foucault is somebody who's really earned my respect, both through individual research papers, but also has a very nice monograph on compressed sensing, which I think is sort of the standard reference for this technology. So I really appreciate that. I was hoping to be present among you during this moment, and some family considerations intervened. I was in Texas for almost a solid year, from August 2020 until midsummer this year. And my wife and I feel it was the year of our lives, like we'll never forget it. I also grew up in Texas, in Houston, and I have pictures of myself from that time with much longer hair than I ever had afterwards. Well, during lockdown, I also got long hair because I didn't go to the hairdresser, and I still keep it as a memory of that time. Our grandson was born in Houston at Texas Children's Hospital in August of 2020. So he, like me, is a proud Texan. And thank you so much for inviting me to give this talk. What I'd like to talk about is a particular paper that's available on arXiv called, the operative term is ScreeNot. I'll explain this as we go along. And I think it's very relevant for data scientists to know about. And we spent a great deal of time simplifying the thinking and maximally simplifying the exposition so that it could be widely used by data scientists, for whom the singular value decomposition is a fundamental tool, and the use of low rank approximations based on it is really a true workhorse of science. Let's see, for some reason I'm trying to, okay. So we're going to discuss a couple of papers that will help us understand this method. The first one is sort of a pre-paper. It was work on finding numerically the optimal hard threshold for singular values. And when it's a square matrix, there's reason one could claim that under a certain normalization matrix, there's an optimal number, single number at which you should truncate. And in the general case, where you don't have white noise, as what's assumed in the earlier paper, there's an algorithm which we will describe. So my co-authors, Matan Gavish and Elad Romanov, are both at the Hebrew University. So as a caricature of matrix denoising, we have some low rank matrix here of rank R. in some relatively high dimensions, m by n. We have noise that's added, and we could think of it as white noise, as indicated in this, or later on something more correlated. And we don't get to observe either X or Y, but what we observe is the superposition of the two. However, what we want is X. And so we need to come up with a process or procedure which will give us an approximation to X based on this noisy perturbation of a low-rank structure. And the workhorse here is definitely singular value decomposition. Gene Golub is one of the names associated with SVD, and there's a nice book on matrix computations by Golub and Charles Van Loan of Cornell. Gene was a Stanford professor for many years, in fact, my neighbor. And in this decomposition, just to introduce terminology, we take a matrix Y and write it in the form UDV transpose, where D is diagonal and U and V are partial orthogonalities. There are just many uses of this, but of course, one of those is to extract the singular values and use them in some way to characterize the elements of the matrix. Very nice article by Cleve Moeller referring to the license plate that the late Gene Golub had on his car, Professor SVD. So for this talk, what we'll be discussing is procedures in the form of form the singular value decomposition, take the diagonal, operate on it in some way. So if I write down for some scalar function, the expression D sub delta, I actually mean the diagonal matrix that you get by applying it to the singular values. Now, when you know the rank of the matrix that you're trying to get, a standard technique is to truncate the SVD at exactly the rank that you think is the true one. And so X hat sub R would be something that's just based on essentially extracting the singular values out of that diagonal piece and then padding the ones beyond the known rank by R. And so you're always going to use the U and the V that came out of your original data, but you're simply going to throw away all the singular values beyond some point. And we'll use the little y notation for the singular values coming from the raw data. So this is the best rank R approximation to the original data, and it is maximum likelihood for Gaussian errors, although there's no theoretical results in MathStat saying that maximum likelihood is in any way a good idea here. Now, if R is not known, so you don't have an established view on what the rank is, it's considered normal at this point to use the so-called Scree plot, where you plot the data singular values in order and then truncate at a thought to be prevalent elbow. So this goes back more than 50 years to the paper of Cattell in 1966. And you can see here the first few paragraphs of the paper, and you can see the figure 1 of that paper illustrating the idea that there are, in this case, eigenvalues, which would be squares of singular values that are way larger than what comes later, which a straight line has been superposed near those eigenvalues in the belief that, roughly speaking, that's the pattern that they follow. And the idea of the Scree plot is simply you look at this plot and it just is obvious to you that you need a rank 6 approximation from this. So this was the first published Scree plot, but there have been many since. Some years ago, in fact, we looked at the Scree plot frequency of citation, and it was at 8,000. I think by now it's above 10,000. And you can see that it entered the language with the advent of the personal computer revolution and became pretty common throughout the period where the Google Ngram viewer has data. And there's just plenty of papers appearing all the time where people are using the Scree plot. And so you pick up some journal, in this case, Nature Photonics, and you read about an application of the SVD where they make some scientifically interesting measurement, and they then in some way calculate the singular value decomposition. So here's the Scree plot, and here are the singular vectors that are laid out in rows here so that you can see things corresponding to the Scree plot, and various interpretations and scientific information is extracted from those singular vectors, which are kind of above the elbow in this plot. So that's an example of this paradigm. It's extremely informal, and I think science has moved on a lot since 1966. But anyway, this is still where we are today. And you can transpose the plot and see the Scree plot in its standard form if you don't like craning your neck. Scree plots are used all over the place in comp bio. And here's sort of the genesis of that approach in about 20 years ago in microarray data analysis, where people make Scree plots. And in this handbook, they explain how to analyze microarray data and how you look at the singular values and look for an elbow, as you see here, and things below the elbow are due to noise, etc. So the problem with all of that is that it's kind of an embarrassment for academic statistics that we could have gotten to a point where for 50 years we allowed people to unexamined, just stare at plots, and no statistician was willing to step up and kind of solve this for them. It's not that there's no literature, it's that there was a lot of literature in statistics, but it didn't seem to be accessible to users, and it didn't seem to have the impact that would make this plot seem old-fashioned. And so it's sort of a challenge to our discipline of mathematical statistics, like how can we let this situation continue? So what we would like is a fully automated solution here with no emotional involvement. And of course, it'd be excellent if it had some kind of full scientific rationale and maybe some analysis that could go along with that. So in the specific case where we know that it's white noise, as we started out at the beginning of the talk, we're going to suggest a simple rule for threshold selection that involves simply taking the singular values and applying this thresholding rule to get this and particular numerical threshold, and just keeping all the singular values that exceed that. So according to this rule, a thresholding rule is something where we keep all the large singular values, and then a threshold selector is a process for analyzing all the singular values of the matrix and deciding where to cut. So Scree plot is sort of an informal rule. We want to come up with something formal that's got a quantitative theory and an understanding. So here's a simple proposal that was in our first paper. If you have a square matrix, if sigma is the noise level is known and the noise is uncorrelated, then in the normalization we prefer, we say you should truncate at 4/√3. So if the noise is just white noise and we normalize things the way we like, it's a very, very simple rule. And if you don't know the noise level, then you look at the singular values, look at their median, just the median singular value that you have, and then use the same rule, but with the plugging in of that. Okay, so very simple, and it amounts to just a few lines of code to implement. In today's talk, we're going to build up and we're going to discuss this so you can understand how there could be such a simple answer in this particular case. And then we're going to discuss the correlated case where the noise is not white, but where there is, once you understand how to think about it, an equally simple and elegant solution that, however, is not just a number, but is a function of all the singular values that we will describe. So there's tons and tons of papers about where to set the threshold, and I'm not going to be able really to give you even just the least window into that. I don't want you to feel that I'm trying to hide from you the existence of prior art. There's many, many papers that you could find, and I'm just mentioning things here. I mention here papers, particularly by colleagues of mine, like Art Owen at Stanford, Sourav Chatterjee, Emmanuel Condez, faculty who visited our department, graduate students in our department, my former student. Like if pretty much everywhere I turn, someone has worked on this in some way. So I don't want anyone to think that this is not, there's been no work at all. That's certainly not my point. Now, in order to understand how there could be such a simple rule, notice that really this field of random matrix theory was sort of born in a way at about the time of the Scree plot, with work of Marchenko and Pasteur in the Soviet literature of the time. And then over the years has developed so that we have a much better understanding of this problem than we could ever have had in 1966. The key thing that we understand now is that there are regularities to the singular values of such a signal plus noise matrix, and there's very, very precise properties that can be described here. So if you just type in MATLAB an expression for presenting the singular value decomposition, at least the diagonal, of a noisy matrix with some signal singular values and some noise. You'll see something where indeed you see the Scree plot that we've been talking about, but if you make a histogram of things, you'll see something more valuable to understand, which is that the histogram is going to look like a quarter circle, and then there'll be these two values popping out away from the bulk. This is called the bulk. And then these are singular values that emerge from the bulk. And the fundamental phenomena that you have here are that inside the bulk, there's a bunch of regularity and there's a lot of deep physics and math analysis to explain the idea that the singular values that you find there are like they're like particles that are self-organizingly arranging themselves under the influence of a kind of electrostatic field that they all experience, which is caused by the presence of all of their collegial other singular values. And so there's this quarter circle pattern that you see here in the case of a square random matrix is it has very deep causes, which can, for example, be understood from the book of Peter Forrester. It's also understood that if we are interested in the ith singular vector in X, which we view as signal, and we look at the corresponding singular vector in Y, which we view as the empirical result, we're not likely to see a perfect alignment. Instead, we see something where as the singular values get smaller, this gets significantly misaligned. And it's also true that the signal singular values appear in very predictable locations, which, or in the output Y, which are not locations of the input X. And so there's all sorts of things going on here. And so there's an asymptotic theory coming out of random matrix theory, but because there's so many entries in even a small matrix, you get asymptotics being very accurate as compared to some other problems that statisticians may be used to. So in this, in the framework that makes the most sense now, we imagine that we've got a sequence of matrices increasing in size with the aspect ratio approaching a constant. And it'll be convenient to have that just a number between 0 and 1. And the singular values, x1 to xr, are going to remain fixed. Under this normalization, it makes sense to leave these things at fixed numbers. Then the signal is in some sense just those R numbers. So it's a fixed dimension. And this model was used by Andrei Chabalin and Drew Nobel of University of North Carolina. And it's the simplest model for exhibiting fundamental phenomena. It was also considered by Patrick Perry at Stanford and is very related to Ian Johnstone's spiked covariance model. Now, a wonderful set of papers about the structure of exactly that asymptotic setup can be found in Journal of Multivariate Analysis. That's a Statistics Journal. These papers are by Florent Benesh-Georges and Rajrao Nadakuditi. And I just think they're of exceptional clarity. So what those papers show us is that, first of all, from the r+1 on singular value, the empirical histogram of the singular values is going to converge to a quarter circle if beta is 1, namely a square matrix, or to so-called deformed quarter circle density if beta is less than 1 and the explicit expression is given. And now we learn from this, what the Scree plot elbow heuristic is really trying to tell us is that you should truncate at the bulk edge. There was no concept of bulk in those days, but as you can see here, there is a bulk edge, and the Scree plot is saying, let's truncate there. Now, the thing is that we need to know more if we're going to evaluate that rule. So one thing is to ask, where do the signal singular values map to? It turns out that signal singular value xi does not map to a yi that's the same. Instead, the yi's are systematically larger if xi is above a so-called phase transition threshold, and the yi's have nothing to do with the xi's below that threshold. So what happens is there are some points that pop out, but they don't pop out in the expected places, and they may not pop out at all if the signal is too weak. Another thing is we shouldn't believe that the empirical singular vectors are in any way representative of the theoretical ones, absent more information. So it turns out that the squared cosine of the empirical singular vectors in this white noise case that we're currently considering has some formulas of how it behaves that depend very much on the singular values xi of the signal matrix. And so in particular, if the xi's are less than about 4th root of beta, there's no signal. There's no relation between the u's and v's and their theoretical counterparts. So we're learning nothing from the singular vectors at that point. So if we're trying to understand the mean squared error that we would be getting if we threshold at some level, remember that 1 plus square root of beta is the value that's being used by the Scree plot effectively. We want to know the MSE that we would have with a given value of the threshold. And it turns out, using the preceding results, you can work out what the asymptotic mean squared error, and it's made of components, one for each signal dimension, and for each singular value, it enters in based on whether the signal is below the threshold or above the threshold. And so we get a closed form expression for the asymptotic mean squared error as a function of t. Now, if you study this, you'll find that it's got a unique minimum, and it's at 4 over square root of 3, which puts it at about, if this is in the case where we've got a square matrix, and that puts it at about 2.33 rather than 2. 2 would be bulk edge thresholding, and this is saying actually if something's close to the bulk edge, it's just too dangerous for us to use it, we don't use it. But if you're a little bit away from the bulk edge, we'll start to use it. And here we consider, for example, a comparison of thresholding based on the true rank versus the use of this optimal thresholding scheme. And we have MSE, and we consider various matrices and different sizes and so on and so forth. And you can see that actually what you might naively think of thresholding at the true rank is actually worse in case the signal's kind of weak. And because you're including stuff that is actually decorrelated from the truth, and you're just fooling yourself. And so the more prudent approach based here is that you only include things that are actually close enough to being aligned with the underlying truth that you're learning something. So you only get signals stronger than a certain amount. If there's a general noise level, we gave you a rule, and that comes from the properties of Marchenko-Pastur, and that gives you the properties we're talking about. So why do we do this? Let's just remember the slogans. First of all, when a data singular value is too small, then its associated singular values are too noisy, and we should not use them. And it just turns out that, let's say in the square matrix case, there's a specific place at which this would be happening under white noise, and it's at 4/√3. And of course, if you know that you have white noise, you can implement everything we've talked about so far in the talk by just these simple lines of MATLAB. Okay, and if you want to know some properties of using this rule, you can see that if we're using this truncation, then we get this guarantee on the asymptotic mean squared error. And many other rules have been proposed, but they don't give nearly the guarantee that you get this way. There is something better, which is to not truncate, but to instead shrink. And then, there's separate papers that we've written about optimal shrinkage, and also papers by others, including, for example, Chabalin and Nobel. So you can do better by not truncating, but truncating is already pretty good, and this is the best choice of truncation. And we can go on and on with possible optimalities that this has. But what I'd like to now discuss is maybe a more fundamental issue for applications. It's fine for theoreticians to propose some generative model and derive an optimality under that generative model, but the essence of data science is we don't actually know a generative model, we just have a data set. And so what we'd really like to have is a method that works without very specific assumptions. You don't need to know that something's white noise and so on. So we're going to discuss a method called ScreeNot, which is in some sense a strict generalization of everything we've been talking about, but it doesn't depend on any specific assumption about the noise. And so we can have a general correlation structure on the rows and columns and so on. Moreover, and this is what's utterly crucial, the user doesn't know the correlation structure necessarily. They just have data. And so the correlation structure is not something that the user has to hypothesize or specify. Another thing that's important for users is it actually available? Like, you know, if it's something that I just click download and run, then it's completely different matter than if it involves reading someone's PhD thesis and, you know, learning to think like they think and learning to speak like they speak and so on and so forth. So part of the no emotional involvement that we spoke about before is that this truly detaches the whole problem away from the aspect of adopting the mindset of the authors. So our goal is to make ourselves as much in the background as possible. Like, people don't even need to know that we ever did this. They can just use the tool. And then finally, this particular tool that we're going to discuss is computationally efficient and can be computed essentially in order n time. Since you have to do an SVD, which is going to cost much more than that, it's essentially cost nothing. And I think the big surprise here is that there's a method which has all these attributes, and on each specific problem instance, it achieves generically the exact minimal MSE if the underlying generative model that we'll discuss is true. So it's easy to use, and it really is unimprovable. Okay, so we'll continue an example across a few slides, and we'll take, it's the example taken from the ScreeNot paper, just very simple example so everybody knows what we're talking about. So let's say we've got one of these m by n observed matrices Y with low rank structure, and then there's noise Z in it. Instead of assuming that Z is white noise, which we had before this in the talk, we're saying we don't actually know. Now, unbeknownst to the user, let's say you and I, behind the scenes, we know the ground truth situation. And in this particular case, X is rank 4 with singular values that, you know, we've picked in some way, with noise that happens to follow an AR1 process in the row index within each column. And let's say the AR parameter is 0.2. Now, the key point is the user doesn't know any of these things. Another key point is this is just one example, and nothing about the AR is important here. Nothing about the specific choice of these singular values is important. This is just so we're all on the same page, knowing what we're talking about. And the matrix size we're taking as 500 by 500. And of course, you know, bigger would be better from the point of view of this paper where asymptotic theory comes in, but it's already quite accurate at sizes even much smaller than this. Now, what the user has got to supply to the code for ScreeNot is the list of the non-trivial singular values of the matrix, just its min, m, comma, n numbers, and one thing, an upper bound on the rank of the signal that you're trying to get. So we're just assuming for this example that the user says, I happen to know that the signal is of rank at most 12. And really nothing else needs to be supplied. And then the method returns a selected threshold, and then you reconstruct your array X hat by just keeping the singular values that exceed theta hat. Are there any questions about the process that I'm suggesting? Okay, so the paper has this very simple example, which is, it's been selected for didactic clarity. So there's just no question what we're talking about. So in this particular case, the underlying data are as we described previously, and figure 1 of the paper. You see the top several singular values. Of course, there's actually 500 singular values. We're just looking at a segment of them. And there are 3 singular values sticking out. One that you might have thought there would be 4, but it's not to be due to random matrix theory effects. The smallest of the signal singular values hasn't generated anything for us. And the algorithm comes back after seeing, well, this data plus the other 470 singular values, and has chosen a threshold exactly at the green dashed line. So when you apply it, we're just going to say we're estimating by rank 3 matrix that has these 3 numbers in it, and then in the core of the SVD sandwich, and those are the only non-zeros. Okay, and now this simple procedure, we're going to say more about how we come up with that green dashed line. What does the ScreeNot procedure do? But I hope everyone is on board about what the inputs and result were. I'm not in a very good position about looking for people with raised hands, so someone would have to just speak up if they have a question at this point. Okay, if not, then I'd like to discuss a formal result about the procedure, and we'll say more about how the procedure is done. So informally, I want to say the assumptions are that we have signal plus noise, and that we have maybe a sequence of such signal plus noise problems where the shape factor of the matrix stays constant as the matrices grow, where the rank of the matrix stays constant at R. And about the noise, the only thing that we're assuming is that the limiting empirical CDF of the noise singular values has compact support. So in particular, very wide range of distributions has this property. So it's there's definitely an infinite dimensional space of such limiting CDFs. And you may wonder, like, the compact supportness may seem unusual, but if we had white noise, the limit of the noise singular values would be related to Marchenko-Pastur or the quarter circle law. That definitely has compact support. And there's a super wide range of matrices with this property. I mean, obviously there are matrices with crazy things as well, but we're handling an infinite dimensional space of possible limiting situations, so it's already something. And then there's one extra thing is that the rank R principal subspace has an orthogonally invariant law, which we could discuss. Now, these assumptions are not the only assumptions that will yield the results that we're talking about, because you could, for example, assume Gaussianity and get the same result. What you couldn't assume is, like, you know, that the Z's have very heavy long-tailed distributions and you know, power laws with small indices or stable laws like Cauchy or something, because then the singular values cease to have the meaning that we're used to, and it actually shouldn't be doing singular value decomposition if that's what your noise is. Okay, so the deliverable that we have in our result, I'm still building up to the result to describe the ingredients. So you recall we require external knowledge of a rank that's larger than the actual signal rank. And we want to consider the hard threshold estimate of X, the estimate based on using the empirical U and V, but then only the singular values exceeding T. And the empirical MSE as a function of T we'll call L sub n of T. Now, this is something that ordinarily we don't know, but it's of much interest to us. We don't know it because we don't know X. That's a thing we would like to know, but we have only noisy data. We do know X hat, but this seems to be completely inaccessible. Well, we're not gonna let that deter us, and we're gonna consider oracle loss, where we take the best possible threshold, and you know, that's saying not just that we want to know the MSE in truth of the reconstruction that we came up, but we actually are so greedy that we're asking for the best MSE we could ever dream of getting by choosing the threshold in the right way. And there's an inf here saying that, well, since we know the knowledge, since we know that this thing is of rank K, we're only going to consider T's that are at least as big as the kth empirical singular value. So this is the smallest possible MSE loss on that realized sample. And it seems so doubtful that you could ever do this, because we don't know L sub n of T, and asking for so much just seems, you know, foolish. So ScreeNot returns for us a threshold with the following property. Under the assumptions that we've outlined above, if in truth our upper bound on the rank really is an upper bound, then we come arbitrarily close to achieving the MSE in all large sample sizes. Okay, but actually even more than that is true. Under one extra hypothesis about the genericity of the singular values, namely that they aren't equal to a certain number, which is defined by the noise and has nothing to do with the signal. And so there's no kind of circularity in this. Then in fact, eventually we just get the exact MSE with overwhelming probability. Okay, and essentially what ScreeNot is doing is, behind the scenes, it's defining a function, psi of theta, theta being the threshold that is variable and you're considering, and it's evaluating this function and looking for the place where it's equal to -4. That the place where it's equal, that gives us the green line, and then the green line you see corresponds over on this plot. We plot here the actual squared error in case where we know the ground truth, and the minimum squared error that you could ever achieve, and green is the actual choice of threshold, and you can see that it's fat in the middle of this bottom step, and that therefore you've done your job. The procedure has various details. You take the top k singular values and you replace them by some model pseudo singular values. These are things that what you think noise ought to look like. You get rid of the original possibly contaminated by signal singular values, and you fill in this noise, the like singular values as if they were noise, according to some formulas that are based on a so-called Tracy-Whittem law out of random matrix theory. You define 4 scalar functions that are known in random matrix theory and are related to the Stilch's transform of the eigenvalues. And then you define this function psi that we mentioned, and then you look for the root of that thing, say by binary search, and then you return that root. And there will be one root, there's no issue there, etc. Okay, that's the procedure. Monte-Carlo verification, just to stress that you could use this in the white noise case where we previously have told you what the answer is, 4 over square root of 3. And we just take some example and run a Monte-Carlo simulation, ask how often do we actually achieve the exact minimum MSE? And you can see as the matrix size grows, the probability of getting the exact minimum goes up and up and up. Okay, so that's, so that's the technology, the result. This is available on GitHub. It's available at the Stanford Data Repository. It really is no emotional involvement. You can just run it. And you just need to provide the singular values and a bound on the rank. Okay, now, if I have any moments left, I'll just quickly say something about the analysis underlying it, because there may be people who love math like me. So let me just ask, do I have a minute to say anything about
Yes, yes, you absolutely do.
Okay. Okay, so back to this paper of Florent Benesch-Georges and Rajrao Nadakuditi. And what they identify, which is for the correlated case, is analogous to what we've already spoken about in the uncorrelated case, that the eigenvalues map to some limit, but the limit is not like the x's that you expect. And the cosines of the singular vectors map to some limit, but it's not 1. And those are some functionals that are actually functionals of the noise CDF, noise eigenvalue CDF, and of beta, and of the putative signal singular value that might be of interest in a particular case. So there are functionals here. They didn't use this symbolism, but this is effectively what they did. Okay, and if we go back to white noise, then those formulas that we've seen before, that's what we have. So it reduces to the formulas we showed in the earlier talk in the white noise case, but it's really much more general. Then the actual definition of the root that we're looking for emerges from a functional theta, which just depends on the noise eigenvalue CDF. And it can be alternately seen to be the root of this equation where the limiting eigenvalue corresponding to signal is related to the underlying guy with a certain cosine. So once roughly speaking, once the cosine is better than a half, it pays to use the signal. And if the cosine is less than a half, you don't do it. And again, for anything with compact support, this will be well defined and will be beyond the endpoint of the distribution. And of course, if you plug in all the machinery that we did, if you just plug in the quarter circle law, you get 4 over square root of 3. Now, empirically, we do a variety of things that I think I maybe shouldn't spend a lot of time on, but in the end, the proof of the pudding is that simple simulations validate that really the underlying loss and a risk function that's defined using the Benesch-George-Rao-Nada-Kuditi line up and get very close to each other, so an analysis can work. There's a variety of continuity properties of theta that we explore, and I'll just skip over those, but these are discussed in the paper. And the key point is that a risk function defined as the limit, its lowest function is always achieved by the functional that we've defined, and there's a continuity property of the functional that says the empirical CDF is converging to that, and so then the loss has to be converging. But because there's a collection of thresholds that occupy a closed non-empty interval that all achieve the same loss, then this thing is converging to the minimum MSE. I gave this talk in Oberwolfach and people had lots of questions, so I just want to be open with you. How do we know the rank? Why should the rank be finite? What if the rank grows with the matrix size? And then finally, why should the bulk distribution G have compact support? So, like the last one is, I think, the easiest, is like if we had Gaussian noise and put in pretty much any like time series dependence, just as an example of like, a huge class of models, then very little problem coming up with bulk distribution having compact support in all of those. It has something to do with sort of turn the spectral density sideways and look at it. As far as why should the rank of the signal be finite? Well, if it's not finite and you've only got a finite amount of data, then you're of course not going to have this exact recovery problem. So obviously, let's take that off the table. However, what you can say is that the functional theta that we've defined is continuous in all the parameters of the problem. And so, and you can also say that the underlying MSE functionals are continuous. And so you instead of exactly achieving the minimum, you're gonna effectively achieve the minimum that you can achieve on that data, even though you don't have enough to achieve everything you would like. So there's going to be some irreducible minimum that you're never going to be able to kill, but you'll be able to kill all of the loss that you can kill. Although articulating that full result, okay, what if K over N goes to constant? You know, okay, so there's ongoing research in the random matrix theory community about that, and there's not elegant results on that yet. You wouldn't be able to come up with such a simple technology in that setting. So anyway, these are the papers that we've discussed, and the last one is in submission. The other ones have appeared, and I'm happy to take any questions.
Okay, thank you very much. So let's open the floor for some questions. Anybody have a question? So there's a question in the chat: to get a good quality theta hat, how critical is it to choose a K close enough to R? If not critical, can we just set K equal minimum of M and N?
Yeah, I don't think, first of all, that's an excellent question. So people should invite you to Oberwolfach. Anyway, yeah, it's sort of important that K is small compared to N for the analysis we have done. So, you know, we're using like R is fixed and K is fixed and M and N are growing. If you're, you know, really interested in other settings, then, you know, that would be, it would be more math, and importantly, it would be kind of beyond the domain where it's been, that math has been taken in the RMT literature. So I still think that this is a very sensible procedure in that case, but I would prefer to just have K be something like, you know, 5% of N, you know, that kind of rule, like we're assuming that the upper tail of the singular values looks like a Tracy-Widom in part of what we do. It's maybe not that important as we show in the paper, but I feel more confident about that little aspect of the software in the regime I just described.
Okay, are there other questions? So I will have one small question. So this question was about K, so a quantity that the user has to supply. You also mentioned that the user has to supply all the singular values of Y.
Yeah.
And so that I guess could be costly to get the full SVD. Is there any way you think that a recipe can be obtained where one doesn't compute all the singular values of Y?
Yeah, I used to think that that was important, but then I feel that computing capacity is sort of outrunning my imagination. So I talked to some people, and you know, I'm assured by younger people that it's pretty standard to do SVDs of size, you know, like 50,000 by 10,000 is like not a big deal anymore. I like, the mind boggles, but if what you're talking about is in the millions, then yeah, maybe so, but oh gee, it's just like what would I do with matrices with, you know, millions of entries? I guess, gee, some kind of a step down procedure would have to be used where you use the power method or Lanchos, and you find like the very top singular vector pairs, and then you work your way down to K. And then you do some analysis after that. That's a very interesting issue. I simply have no answer for you. I mean, I just have not worked with matrices of that size.
Thank you. Two more questions have popped up in the chat. So the first one is the signals in the examples are pretty evident. In that case, simple eyeballing will work. When noise increases, it might happen that mean distance to bulk to signal goes to 0 as n goes to infinity. What could be a good conditions on that distance?
Yeah, so I'm not sure if I said it clearly enough, but let's say we had white noise. First, these questions are all spectacularly good, by the way. So thank you for the questions. If I have a square matrix and it's normalized the way we prefer, and say there's white noise, so then the bulk is going to extend out to 2. And then this threshold is going to be at 4 over square root of 3, which is kind of 2.33. So it leaves a pretty big margin. Margin is like, you know, well over 10% between those. So in that setting, if the signal is really shrinking down towards the bulk edge, it's going to be thresholded away. And so that's part of the attraction of this whole approach, is that it's saying if the cosine between the signal singular value and the singular vector and the corresponding empirical singular vector, if that cosine gets below 1/2, it's worse to use that thing than to not use it. And that's 1/2. There, you know, a lot of people might imagine they should still try and use it, but at least for MSE, you shouldn't try. And so this is telling you that these kind of close cases, you simply shouldn't pursue. They're only going to exert an MSE penalty for trying to get things that are, you know, that marginal.
Okay, thanks. And the final question is from the chat: would data normalization affect the theta estimate?
Would data normalization have
affect the theta estimate?
Yeah, okay. I want to also make clear, this is a good point. Elad Romanov and his co-author Will Lieb have another paper that could be mentioned, which is about the importance of normalization. So what we're talking about right here is what to do when you're committed to this, this particular normalization of the matrix. Now, if you're allowed to do row and column scalings, it turns out that you can improve the accuracy of the singular vector estimates. And so, they have a paper on kind of optimal row and column scalings. And so you might want to, precondition the whole estimation problem by following their ideas. But even if you do precondition in some way inspired by them, you still need to use something like this, because you don't know that their assumptions are strictly strictly speaking correct, and this one doesn't need such assumptions. So you scaling will give you, scaling rows and columns will give you potentially better results, but you still then need to use something like this. So this could work together with some kind of scaling. An example of scaling that you could do is try to have rows be all of about the same length and columns be all of about the same length. And there's a recent paper out of Yuval Kluger's group at Yale with Boris Landa and others who give an example of this in the case of Poisson data, where they propose a scaling method.
Okay. All right.